Good evening, ladies and gentlemen, and welcome to the SAIEE Energy Storage Chapter webinar. Tonight, we'll be discussing the value of long-duration flow battery for energy storage. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Energy Storage Chapter playlist. In the chat function, you will see there's a link to subscribe to this channel. It is free, so I encourage you to subscribe. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our host for tonight, Professor Pat Naidu, who is a Research and Innovation Chair, Green Economy at University of Johannesburg. Dr. Naidu is a Professor of Research in the Faculty of Engineering and the Built Environment, University of Johannesburg. He is a Fellow of the South African Academy of Engineers, a Fellow of the South African Institute of Electrical Engineers, a Senior Member of IEEE, and a member of IET and SEGRE. He is a Registered Professional Engineer and a Specialist Consultant in Electrical Energy and Power Systems. His current research interests are in sustainable development as driven by the green economy and Industrial Revolution 4.0. Dr. Naidu's 4-decade industrial career was with the Electricity Supply Commission in South Africa, from engineer in training to non-executive director. I hand you now over to Professor Naidu.
Thank you, Webinar Director. Thank you and good evening, colleagues. Thank you for your attendance this evening. Firstly, on behalf of our Chairman of the Energy Storage Chapter, Professor Chandima Gomez, we would like to extend our appreciation to fellow member Chris Joubert of Africa Energy Solutions for his facilitation of this webinar that we are hosting this evening. I would like to introduce our guest speaker, Mr. William Sproul, who is the Vice President of Business Development at Energy Storage Solutions Incorporated, based in Wilsonville, Oregon, USA. Mr. Sproul is actively promoting disruptive technologies, and today his passion is in developing long-duration energy storage solutions. We would like to develop clean energy solutions for clean energy storage, such that we provide inexpensive, safe facilities for societal application. Mr. Sproul is going to talk about flow batteries using iron salt water electrolyte, and I will now hand you over to Bill for his presentation. Thank you.
Thank you, Pat. It's a pleasure to be here this evening and to have an opportunity to speak to you. I will hopefully be sharing my screen here. Do you see it fine?
You can just, yes, there we are. Thank you.
Okay, thanks. So what I'll talk to you about this evening will be long duration energy storage. That's the focus that our company has with the iron flow battery technology that we've developed over the last 10 years or so. And with that, I will jump into it. We'll have an opportunity to answer questions after the presentation, as I understand it. So real quickly, ESS is headquartered in Oregon, in the western part of the United States. We founded the company back in 2011 and have been focused exclusively on developing the iron flow battery technology for commercial and utility scale type applications. And we've deployed a number of systems that I'll talk about, and we're now at the stage of ramping production dramatically over the next year or so. We should have a couple gigawatt hours of production capacity online by the end of next year, 22. So let me start talking about the changes in the grid and the reasons why long duration storage are starting to become an important factor in adapting to those changes. Obviously, these are fairly well-known issues that are on the grid, and this, it's irrespective of what part of the world you're in. A lot of these issues are being felt throughout the world. Obviously, aging infrastructure, the impact of severe weather events, and probably one of the bigger drivers for long duration storage is the increasing penetration of renewables throughout the grid and the corresponding reduction in coal-fired, gas-fired, spinning reserve type generation systems. And obviously the growing electrical demand is a very, very big factor, and we see that continuing as we start to evolve transportation to more electrified transportation. So all those factors are coming into play, and we think that long duration batteries, energy storage in general, will have to be a major element to stabilize and give resiliency to the grid over time. Obviously, the needs that long duration storage address will be stabilizing a grid that is becoming less or more intermittent with renewables. As we start to penetrate the generation side of the grid with more intermittent renewables, the need to stabilize and create a good stable 24-hour energy source is coming. And then there's definitely throughout the world a trend toward decentralizing and moving toward more microgrids and giving localized control to the energy generation and delivery. So in our opinion, what long duration storage is, it's probably in terms of hours is 4 hours or more. The part of the market that we are addressing is that interim part of the duration, which is 4 to 12 hours. There's many technologies that are addressing the shorter duration, namely lithium ion, and the longer duration, more seasonal and multiple day type storage applications. But our focus is really on this 4 to 12 hour region, which is where you would have daily cycling and be able to perform multiple functions during the day. Obviously, being able to smooth out and give the resiliency to the grid with more renewables on it is a big factor coming forward as we take more and more of the fossil fuel plants offline and rely on the renewable type generation. So where we fit in the long duration world and where we see the real needs starting to develop is those durations up to 12 hours, where the not only does the, whoops, excuse me a second, I pressed the wrong button here. So where the use cases are maybe multiple, you maybe have ancillary services as well as bulk shifting of energy, and the need for resiliency is very, very keen. Our approach that I'll get into a little bit with the iron flow battery is very focused on the levelized cost of storage over time. So we go to market with a technology that is a 25-year asset, very low maintenance requirements over time, and the key would be that we're delivering a low cost of storage over that 25-year period. One of the key elements of the iron flow battery that I'll touch on is that the electrolyte, being iron salt water, is very inexpensive. And so the incremental cost of adding duration with an iron flow battery is very low. You can see it's in the order of $20 per kWh. So what that enables is use cases that may have relatively low marginal value or revenue potential can be added to those use cases that have high revenue value or high value. And because you have a very low marginal cost, you can increase the overall return on the investment for a energy storage project by adding those other marginal, lesser valued use cases and increase the use of it. The flexibility to do multiple use cases with an iron flow battery, or any flow battery for that matter, is something that isn't necessarily there with lithium ion. Usually to preserve warranties on lithium ion, you have to abide by pretty strict cycling and depth of discharge requirements, which get in the way of using it for multiple things every day. With most flow batteries, like with lithium ion, very fast response. The iron flow battery that we have can go from 0 to full power in less than a second. So that can address some of the frequency regulation and voltage support, ancillary service type requirements on the grid. And there's no degradation with our technology, so that greater than 20,000 cycles, virtually unlimited number of cycles, both shallow and deep discharge. Being an aqueous solution, the iron flow battery is safe, non-flammable. There's no chance of thermal runaway with these, so that takes away one of the safety concerns that exists and we see from time to time with lithium ion. And one of the bankability elements that we've been able to put in place is backing the extended warranty with insurance policy. And we have an arrangement I'll touch on a little later with Munich RE to back the technology and give peace of mind to the long life aspects of the iron flow battery. And obviously sustainability is an important element of it, using abundant materials, iron, salt water, a lot of plastics in our system. It's easily recyclable at the end of life, and it does not cause us to go dig up rare earths and more precious materials around the world to satisfy it. So we're pretty pleased that we can bring a very safe, resilient, and sustainable solution to the market for long duration energy storage. Here's just a few of the compelling elements on the performance side. Typically lithium ion would be giving you up to a 4-hour type battery and limited cycles every day. Our sweet spot, as I mentioned, is the 4 to 12-hour range. We do have a 25-year asset life, really unlimited on the cycle side, so that you don't have degradation in the energy capacity over time or the need to go augment the battery over time. Fairly wide operating temperature. We operate at 40 C in the battery, so we can go into very warm environments and not have to air condition the system. So that's one less mechanical element that has to be maintained over time, and reduces the auxiliary loads that are required to keep the system operating. And I've already touched on the safety side of it, which is probably pretty self-evident, being an aqueous electrolyte solution. A number of other technologies that are out there for long duration. You can see some of the attributes. Over on the far right-hand side, obviously pumped hydro has a lot of attributes. The environmental siting of those is one of the downsides, or one of the major issues that you have to deal with. But you can see that in many of these areas, the iron flow battery has some very significant attributes. Vanadium and zinc bromine flow batteries have a lot of attributes, but there are some limitations, and the toxicity of the electrolyte and the cost of the electrolyte are some of the issues that you have to deal with there. So on the cost side, I mentioned that the marginal cost of adding duration with a flow battery is probably one of the key attributes. With a lithium ion, you can obviously go up to 8 or 10 or 12 hours, but what you're doing is you're adding cells. And so it pretty much flatlines the capital cost as you extend the duration out beyond 4 hours. And obviously what we're doing on a flow battery is we're adding electrolyte. When that electrolyte is iron salt water, it's very inexpensive. So you can see that it drives down the dollars per kWh capital cost on here. And I mentioned earlier the LCOS. There's a couple of different versions on here. At 4 hours, you can see a lithium ion typically is going to be about 7 cents per kWh on a LCOS basis. This would be a 25-year type life, or you're maintaining the capacity over that life by doing augmentation, and you're cycling the battery every day. Whereas it's about 2 cents, about 5 cents on the 4-hour version of the iron flow battery. And then when you add that electrolyte to get up to 12 hours, you can see the dollars per kWh, or the cents per kWh, if you will, drop very low. So when you couple that with very inexpensive renewables like solar, if you have a large solar field that's producing at 2 to 3 cents, I'm speaking US cents, per kWh, and you have a levelized cost of storage down in the 2 cent range, your cost of energy going through the battery can be a very low 4 or 5 cent per kWh range. So I touched on the sustainability. The one thing I didn't mention is one of the things that people don't think too much about, and certainly is consideration for renewables and batteries, is what amount of CO2 or precious metals or electricity is required to produce these assets. And we're quite pleased that to produce an iron flow battery is less impact, if you will, than any other flow battery out there, and certainly less impact than a lithium ion, which has to mine some fairly precious materials. A couple of case studies to show you how we're applying it in the real world. In California, we have a microgrid. It's a utility customer that, because of wildfire risks, they do public safety power shutdown events, which basically will shut down a section of the grid for what could be a couple of days as high winds and dry conditions cause them to depower the grid so that they have no chance of starting a fire. What we have gotten involved with is a microgrid solution for critical loads in a small community. This particular one, we're providing power to a fire station, a medical facility, and a gas station. And that enables people to get critical services even in that power shutdown condition. This particular case, the situation where we need to be available for potential wildfire shutdowns is about 3 or 4 months in the fall. The rest of the year, the utility is using this microgrid to do bulk shifting of PV to the peak hours in the evening in California, and also using it for participation in the broader grid with ancillary services. So this application gets a lot of use, a variety of use cases, and it has about 10 hours of duration to carry the critical loads from day to day during these multi-day power shutdown events. Another case that we have is in southern Chile and Patagonia, and that is a run-of-the-river electrical generation plant. But when the river water level gets low, they have to supplement that with a diesel genset, or when the load of the community nearby gets above what the river can produce, they have to use a diesel genset. So about 60% of the year is covered by a diesel genset at some power level. And by putting in long duration a flow battery there, we can store up the excess hydro when the demand is low, and then eliminate the need for the diesel genset. I think the estimation is that we've gotten it down to about 15% of the total year requires the diesel genset to supplement it. So it's a significant reduction in the use of diesel gensets and this remote off-grid, basically off-grid community type application. The technology itself, we started working on back in 2011. You can see on the right side, the critical intellectual property deals with the power module and dealing and eliminating the issue of any degradation of the electrolyte or the power module over time. We have what's called a proton pump that deals with side reactions that happen every cycle, and that automatically cleans up and keeps the electrolyte fresh from cycle to cycle. That's where a lot of the innovation has happened in our technology, and we've evolved that technology from first systems going out in 2015 to our second generation of product is going out this year into both containerized applications and what we call an energy center. And this is a quick look at what a power module looks like, which is kind of the core element of the iron flow battery. I think I've mentioned most of the attributes there, but basically relying on iron salt water to carry the iron in the electrolyte form, and then when we're charging the battery, we're actually electroplating that iron onto the negative electrodes in the battery modules. And then when we discharge the battery, we're deplating that back into solution. So that proton pump and the innovation around it is what's keeping the electrolyte healthy over time. We have 2 platforms we're going to market with. Basically, for the behind the meter market, we have a containerized solution that you can see in the middle there. The electrolyte is kept in a tank, which takes up about half of this 40-foot ISO shipping container. The battery modules I showed you a second ago are stacked on the other end of the container, as is the battery management system, the DC-DC electronics, and for an AC version, we have string inverters in there as well. The electrolyte health management system and the electrolyte pumps are in that other half. So this ends up being a turnkey shippable system that can deliver either DC or AC power to a facility or to a microgrid. And that's we've deployed quite a number of these. We're shipping a number of those as we speak in our Gen 2 version of this. The other platform is taking the same components. We take the tank out and we put that outside of a building, and we take the battery modules and the pumps and DC electronics, BMS, all are mounted on a skid that we build in a building. This is more for utility scale, front of the meter type applications, a more cost-effective way of bringing that to market. This gives you a view of the containerized solution that we call the energy warehouse. You can see in the picture in the upper right, the battery modules are stacked up in there. On the far right side is where the electronics are. Again, this operates at about 40 C, so we don't need to have any air conditioning. There's some ventilation. You can see the fan on the door in that picture, and a variety of applications, primarily in the US to date, but we are starting to ship, as I mentioned, to South America, Australia, and we'll have some units in Europe later this year. This is the Energy Center. You can see all of the core components, same core components as in the containerized solution, are mounted on this powertrain, and the powertrain is shipped from the factory to the site. We work with contractors, EPCs, to rig them into place, do the plumbing, electrical, put a building around it, and interconnect the tanks. The beauty of this approach is we can put as much electrolyte on the site as required. The typical capacity is 12 hours at rated power, and you can see a layout on the lower left there where we are putting 10 of those powertrains into a building, and each of those powertrains has a corresponding 3 electrolyte tanks, 2 positive, 1 negative. So on roughly a half acre of space, we can have 36 megawatt hours of energy capacity, being able to cycle that every day. So 12 hours of charging, 12 hours of discharging is possible in a project like this. The last thing I was going to touch on, I touched on it earlier, is obviously a big part of getting a new technology into the market is bankability. And we do have this relationship with Munich Re that extends a investment grade backing of our warranty for financial security. And there's a separate product that they offer on a project by project basis that will basically back the business continuity aspect of servicing that warranty and the O&M over time for a specific project. So we've got several customers that have taken Munich Re up on that, and they have the financial backing for their particular project. We are doing some projects with the US Export-Import Bank, which offers some very attractive financing. And actually, we're working with a developer in South Africa, and they're evaluating the financing via the Export-Import Bank for a large project that is potentially being developed over the next couple of years there in South Africa. And we have the ability to develop projects, but quite honestly, our focus is on the iron flow battery equipment manufacture and sale, and we like to work with developers and EPCs and end customers to make that be an element of their energy storage portfolio. So with that, I will let this go to questions. I thank you for your attention and be happy to answer and delve into deeper on questions.
Thank you, Bill. Thank you. That was first class. First class. Thank you. Very clear.
Good.
Colleagues, I'm here. Right. We've checked on the questions poll, and there's no questions.
Okay.
So let's
I
find
may
some.
I
We
may
can't
have
let
zipped
go.
through it quickly. If there's more that you'd like me to dwell on, I'd be happy to.
Okay, there's one now, Chris here. Yeah, the one question is from Gurga, Sai Gurga. Are there any funding options? I think you have mentioned that now. Maybe you can mention an example on that.
Yeah, so there's obviously several ways that energy storage can be brought into a project. The one that I mentioned earlier, using the Ex-Im Bank, the U.S. government has a Ex-Im Bank that will back U.S. products for export, and there's really two levels. On a very large project, they can step in and be the U.S. government agency can be the financier of that project. On smaller projects, I want to say $10 million or less, they use commercial banks where they will provide a guarantee to that bank so that they can enable much lower cost financing than might otherwise be commercially available. I mentioned that we are engaged with a developer in South Africa that is looking at an offer from the Ex-Im Bank. It's very attractive. I think if I can recall some of the terms, I think they can finance up to 85% of a project. As much as 20% of the cost of that project can be local content. So it's not just the equipment that's being shipped from the US, but it can include local content. And I think the term typically is in the 7 to 10 year range on the Ex-Im Bank financing. There's plenty of other commercial financing entities that can be brought to bear on projects for leasing opportunities or things like that as well.
Thank
There's
you.
another question from Paul de Villiers. What is the cycle efficiency of the flow battery? And I think
a good question. Good question. I should have touched on that. So most flow batteries are not as energy efficient as a lithium ion. Our round trip cycle efficiency is 70% DC-DC, and that includes all of the auxiliary loads that would be required. So obviously in the containerized solution, all of the auxiliary loads are inside the container and are supported by the DC converters and the onboard inverters. In the energy center, the building auxiliary loads are included in that 70% round trip efficiency.
Thank you.
Then another question from Edgar Capes. Is there no O&M items needing routine replacement during its life cycle, such as membranes, etc.?
A good question. In our particular design, there are not. That power module that I showed you is totally glued up so that it, it's designed to last for at least 25 years. The whole electrolyte system is a closed loop system, so we don't have to add any electrolyte over time. Part of what's going on with that proton pump is we are keeping the electrolyte fresh by putting things like hydrogen back into the electrolyte in real time so that we're not losing anything cycle to cycle. We do a periodic maintenance, I'd say maybe once a quarter, where we will fully discharge the battery and we can mix the negative and the positive electrolyte. That's another way that we keep it fresh. over time. And so there's really no augmentation that has to happen. The replacements might be on air filters for the ventilation system, depending on the environmental conditions it's in. Maybe some sensors and things like that over time, but very minor replacement type elements. Pretty much all of the balance of plant is commercial, off-the-shelf types of materials. We use commercial water pumps, PVC plastic plumbing. It's a very simple yet elegant design, I guess. So it's very easy to maintain over time. And as part of the extended warranty, we do offer that maintenance and monitoring of the system.
Right, and then two questions from Christo Botha. He's from Element Consulting Engineers. Hello, Christo. First one is, what would be the typical footprint for a 320 megawatt, 1140 megawatt hour system?
320 megawatts. So our footprint of that energy center I showed you, which is kind of the battery in a building, it's really driven by the power level, and we're about 6 megawatts per acre. So 320, what are we talking about? A 12. So we're probably about 50 acres if you keep it at a single level for 320 megawatts. The duration can be up to 12 hours at rated power. We actually have another 20% of electrolyte in there that is available every cycle at less than rated power that could be tapped into each cycle. But what really drives the footprint is the power requirement. And we do have the ability to stack those power trains too high, which could possibly reduce the footprint about 25%. That's a big project.
That's a big one, yeah.
Yeah, and then another one from Christo Botha. Any plans for SA local content in terms of system manufacturing or assembly to compete in government programs?
Okay. Currently our manufacturing is here in Oregon. We will have that up to about 2 gigawatt hours of production capacity by the end of next year. We have publicly announced that we will be putting manufacturing in place in certain regions of the world. One has been already announced that we're doing something in Australia. I think as the markets develop and the demand increases in a certain region, it would make perfect sense to have some manufacturing in Africa as that market starts to develop for long duration storage. And there's no reason why we wouldn't be sourcing portions, if not all, out of South Africa. Certainly the electrolyte, iron salt water, is available anywhere in the world, so that would be one of the elements that could be locally sourced very quickly and easily.
Then another question from Stephen Mavunyana. What have been the challenges in meeting the ancillary services requirements of various grids using the flow battery?
So I mentioned the response time is important for those ancillary services like frequency regulation and things like that. The inherent response time of the iron flow battery at the DC bus, so at the low voltage DC bus where the reaction is happening, is very fast. It's like 10 milliseconds. What makes us say that the system response is 1 second is the communication that goes on between the inverter and the BMS to get the battery to react to a command. So we have a 1 second reaction time. That should satisfy most ancillary services out there. It obviously doesn't serve as a UPS seamlessly carrying a load, but to perform ancillary services for the grid, it's very capable of doing that.
Thank you.
Good. I think we have time for a few more, which I not see coming up, but I have some of my own, which I think may be topical. On this topic of long duration storage, we see a lot of talk about long duration storage and flow batteries from the side of the US government and some of the states, especially California. Do you see this now as a trend going forward worldwide?
Yeah, that's a good question, Chris. It's a trend that really started to change, I'd say, within the last 18 months in the US. And what really seems to be driving the extended duration requirements are the penetration of renewables. And a lot of states, individual states in the United States, have started adopting mandates for zero carbon emissions or reduction of carbon emissions, going to 50% renewables, going to 100% carbon-free by 2040, or various dates are being set by these states, and that's causing the utilities to remix their generation sources. So as you're seeing in a lot of places around the world, you're certainly seeing in California and Oregon, where I am, and a number of other states, our coal plants are being taken offline. Even natural gas peaker plants are being discouraged, and there's a strong push for renewables. With that, you're bringing on less stable, more intermittent type generation sources. And a 2-hour or 4-hour lithium-ion battery is not going to be able to fill the bill. You could extend that lithium-ion out to 8 or 10 hours, but economically, that's not the answer. So we're seeing a lot of the market shift to 6, 8, 10-hour type requirements in the US, seeing it in Australia coming on in the next couple of years. And some of the other parts of the world, South America, and even in Africa, we've got a number of projects that we're engaged in discussions with, where the resiliency that's needed from long duration storage is starting to creep into the requirements. I think the other aspect, which is kind of interesting, a lot of the utilities, we kind of see immediately jump to 4-hour type duration requirements because they know that's the sweet spot for the dominant technology in energy storage, lithium ion. And they don't, one of the challenges we have and others in the long duration storage space is educating the people that are writing the requirements that there is technology that enables you very economically to have longer duration use cases and to stack multiple use cases with the same asset. And that seems to be starting to resonate with a number of the people writing the requirements behind these RFPs and so forth.
Good. There are more questions coming in now. One from Edgar Capes. He asks, does it then mean that the utilization functions such as frequency and fast voltage control is limited? I think that's in response to the round trip efficiency.
Well, the round trip efficiency is a factor if the cost of the electricity that you're charging with is expensive. As an example, if the electricity is inexpensive off of a large solar field, it might be 3 cents a kWh. If you're losing 30% going through a battery, you're talking about a penny of cost versus if you had grid electricity at 10 cents kWh, you're talking about 3 cents. So the economic impact of the round trip efficiency comes into bear if you're using grid electricity that's expensive to charge that battery. It doesn't have much impact on a project pro forma if you're using very inexpensive wind or solar type energy to charge the battery.
Yeah, there's another question from Leon Drotsky. What is the impact of temperature on capacity?
So there's no impact on, so if I understand that right, energy capacity, there's really not an impact of the temperature on the energy capacity, because what we're doing is we're electroplating iron. We can do that over a fairly broad range of temperatures. The most efficient spot is about 40 C in the battery. And we are an exothermic reaction, so we create our own heat. We're self-heating. We have a large tank of water-based solution sitting there at 40 C, so we don't change our temperature very much. We can go into very cold environments or very hot environments, and the operating temperature isn't impacted very much. Once we're fully charged, we have created a thin film of iron on all the negative electrodes in each of the cells. So we can sit there and basically be in standby and not worry about any temperature changes, and then come back and get the unit heated back up to, say, 25 C, and we can start operating again and discharging. So there's not a lot of temperature impact on the energy capacity, I would say. There certainly is on the efficiency of the chemical reaction, the electrochemical reaction that we're doing, but because we are self-heating, we pretty much maintain that temperature ourselves during cycling.
Good. Then one from Montague Miller. What are the electrode materials?
There's a lot of plastics, some graphite type carbon graphite materials in there, relatively low cost materials. We tap into some of the existing materials for other chemistries, and really don't have to put any exotic or precious materials in there.
Good. Then another one from Christo Botha. What is the typical lead time to source a system on site in South Africa?
So the lead time right now, we're fairly fortunate. We have a fairly nice backlog of systems. We're in the throes of ramping up production. So we have about a 10 to 12 month lead time right now on delivering systems. As we bring up this automated manufacturing here in Oregon, that will shorten up. I would say this time next year, we would hope that our lead times would be down in the 3-month type range for the containerized solution. The battery in a building are really customized to specific projects, to specific locations. So the construction lead time is probably in the 6-month time frame for a smaller project. That 320 megawatt project probably takes a little longer than that to construct.
And then another one from Christo Botha, which I think is interesting, is have ESS evaluated compliance with the SAP ESS grid code?
So I assume that's the South African grid code? Yeah.
Yep.
Chris, you might be able to help me on that, because we've talked a bit about the requirements there. We're certainly certifying to UL and CE standards, IEEE standards around the world. I'm not familiar myself with any unique aspects of the South African grid code, but Chris, you may have some thoughts on that.
No, I'm quite sure that our standards is not excessive in any way. It should follow the international standards, and definitely follow up. Prof. Pat, do you have background on that?
No, it's most likely SAN standard in synchronism with IEC, so it should be internationally sound.
Mm-hmm. Yeah, and you know, there's now fire standards as well that we comply with, and obviously being an aqueous solution, it's pretty easy to comply with those standards.
Yeah, but I think, Chris, in terms of formalities, we could check that out locally for you.
Yeah, no, we'll definitely look at that. Then another one from Murray Selkirk. Environmental concern around a spillage. What mitigating systems are there to prevent a major spill? Would we need to have the units in a bond-walled area? Good one.
It's very much up to the local authorities. The installations we have done have ranged from, in Southern California, we had a containment pad that the containers sat on. The containers themselves are a secondary containment for a period of time. But in Southern California, they put I think it was about a 6-inch berm around the containment or the pad that the container sat on. We have other applications out in Nevada. We're sited at an airport out there. We're just on a crushed limestone bed. So the electrolyte is iron salt water, pH in the 3 or 4 range. Basically, you have rust water once it's exposed to oxygen, and can be cleaned up with a power washer if you need. It's environmentally, it can be just diluted and put down the drain. It's not anything hazardous.
Yeah, it's certainly non-toxic.
Non-toxic, definitely.
Good. I think there's only one more that I would like you to reply to. Mm-hmm. When we look at rural areas into Africa, there's always the concern that maintenance will be problematic. What is required for routine maintenance? What kind of qualification do you need to be able to handle this? I think that is something that some people think may be worrying.
Yeah, so the unit is pretty self-maintaining. What we do want to have in place is some access to the internet. So one way or another, in a remote location, if we can have the units speaking to the internet, then we have 24/7 monitoring capability of those units. There's a whole bunch of sensors and data points that are being downloaded so that we can get any alerts if there's an issue with that unit. In terms of routine maintenance, we're doing 6-month inspections. We will change air filters, as I mentioned, if required, if it's in a dusty environment. There's really no augmentation that we have to do. You know, there's periodically we may touch up if there's any rust forming on the container or something like that, just to keep it pristine over the 25-year life. But it's typically a 6-month maintenance visit to do inspections and visually see that everything is operating all right. As I mentioned, with the internet connection, we're constantly monitoring it electronically.
Excellent. I think that concludes the question, the Q&A.
Thank you, Chris. Thank you for handling that. Thank you, William, for the answers. And I think you certainly have put a product on the table that is by design, simple, straightforward. And I think it's certainly a product that can be welcomed into the South African and African market. There's space for it. I think the emerging developments locally in terms of promoting deeper application of renewable energy, intermittent renewable energy, and also competitive market operations will certainly support the product, and its future looks extremely bright locally.
Good. We're excited to look at opportunities and bring the iron flow battery to South Africa. We think the markets, including South Africa, are moving that direction, and appreciate the opportunity to introduce this today.
No, thank you very much, and thank you to Chris for the introduction and for the facilitation. Colleagues, let me hand you back to the webinar director for the next steps. Minx, over to you.
Thank you, Pat, and thank you, Chris, and most of all, thank you, Mr. Sproul, for availing the time. I know it's early morning there for you in the US. Thank you for your very informative webinar, your presentation. Ladies and gentlemen, you see in the chat box I've put in the SAIEE website where you can go and register for the energy storage chapter's next webinar on energy storage. It's a debate on energy storage versus fuel cell. Please go and register. That takes place next Wednesday the 15th at 17:30 South African time. For everyone, for your attendance, thank you very, very much. As I said before, the recording of this webinar will be uploaded on the SAIEE TV channel under the energy storage chapter playlist. Go there, register, it's free, and we hope to see you soon. Thank you, have a very good night, and goodbye.